Have scientists finally seen what's inside a black hole? Before we begin today's journey into exploring the universe, I have a question for you. When it comes to black holes in the universe, what comes to mind? A. A completely empty space where nothing exists. B. A gateway to another era or another universe. C. A region containing immense energy and crushed stars. D. A place holding the secrets of the universe's origin. Let us know your answer by commenting below. Now, let's get back to the video and join scientists as we uncover the mysterious yet fascinating truths about this cosmic phenomenon. Black holes have earned terrifying nicknames, such as the monsters of the cosmos. A black hole is akin to a giant vacuum cleaner that can devour everything in its vicinity. Instead of running on electricity, it uses immense gravitational force, pulling anything that gets close enough into its depths. What happens to those objects afterward? Do they continue to exist or cease entirely? That remains a mystery beyond our understanding. A black hole is like a vortex in the universe, straddling the realms of space and time. It consumes matter relentlessly, allowing nothing to escape its grasp. The more it devours, the larger its mass becomes. Scientists have hypothesized that if a black hole were to approach Earth, it would inevitably pull our planet into its abyss. So, what exactly is a black hole? Does it truly exist? And how have scientists proven the existence of such a phenomenon in the universe? Black holes have been proven to exist. They are no longer just a subject in science fiction stories. Scientists first proposed the idea of black holes 3 centuries ago. At that time, black holes were merely speculative concepts based on the physical laws understood by scientists of the era. Nobody could have imagined that such mysterious and incomprehensible entities could exist in the universe. In the 18th century, British astronomer John Michel and French astronomer Pierre-Simon Laplace discussed a strange mass in the cosmos capable of pulling light into itself using its own gravitational force. Imagine why rockets can escape Earth's gravity. They move faster than the gravitational pull of the planet. However, in the case of this mysterious mass, nothing can surpass its gravitational force, not even light. This means that light cannot escape a black hole, making it impossible for us to observe a black hole as easily as we observe stars. This foundational idea laid the groundwork for what we now know about black holes. In 1916, the brilliant physicist Albert Einstein completed his general theory of relativity, which described how gravity affects space and time. Einstein proposed that space and time are interwoven into a single fabric that is elastic. Planets rest on this fabric and distort it due to their mass. Imagine placing a marble on a stretched piece of fabric. If the marble is heavy enough, it will cause the fabric to dip wherever it moves. Now, consider this fabric as the combination of space and time. When the fabric dips, it means that space and time are being bent. But what would happen if an extremely massive object appeared? It wouldn't just create a dip in the fabric, it would create a deep depression, almost like piercing through it. This depression is what we now call a black hole. This means that in the universe, there could exist an object with a gravitational pull far stronger than Earth's. If a beam of light were to pass near this depression, the light would bend and be pulled down instead of traveling in a straight line, leaving behind a long streak. However, Einstein didn't believe we could detect black holes in the universe because such objects would be incredibly difficult to observe. Just 2 months after Einstein published his general theory of relativity, his groundbreaking ideas continued to reshape our understanding of space and time. The German scientist Karl Schwarzschild was the first to find an exact solution to Einstein's equations, and he was the one who defined what we now know as a black hole. However, The technology of that time was not advanced enough to provide evidence of a black hole's existence. Nevertheless, scientists worked tirelessly to uncover more information about this celestial object. Years later, NASA provided the following definition of a black hole. A black hole is a celestial object with gravitational forces so strong that nothing, not even light, can escape from it. Contrary to the common imagination of a black hole as a deep, well-like pit, a black hole is actually a black spherical object. The region surrounding it, known as the accretion disk, emits electromagnetic radiation. Around the black hole is an area called the event horizon, a remarkable boundary that acts as a one-way path. While it is possible to cross from the outside into the event horizon, nothing can escape once inside. The deepest part of the black hole is called the singularity, a place where all known physical laws break down. This mysterious core remains one of the greatest enigmas in modern science. The reason a black hole is not a literal hole, but a spherical form, lies in how black holes are created. Their immense gravitational force pulls matter in from all directions, compressing it into a spherical shape that defies our conventional understanding of space and time. Scientists believe that black holes are formed from the explosion of a star. Stars in the universe are massive collections of hydrogen atoms, where nuclear reactions constantly occur in their cores. These reactions produce heat and light, making the stars shine. At the core of a star, nuclear fusion occurs, where hydrogen atoms are crushed into helium atoms. This reaction generates immense energy, which counterbalances the gravitational force exerted from outside. However, in stars with masses many times greater than that of the Sun, the temperature and pressure in their cores can reach billions of degrees. This allows the fusion of heavier elements like oxygen, sulfur, and silicon. Eventually, the fusion process creates iron. Unlike lighter elements, iron does not produce energy during fusion. As more iron accumulates, the energy production inside the star and the gravitational force outside become increasingly imbalanced. The star stops burning, and under the influence of gravity, its core collapses. The star explodes in a supernova, an event where the explosion can eject material at speeds up to 1/4 the speed of light. If the remnant core of the star is sufficiently small, it becomes a neutron star. But if the core's mass is too great, it collapses further into a black hole, an object with gravity so strong that nothing, not even light, can escape it. For instance, our Sun does not have enough mass or gravitational force to become a black hole. If the Sun were to reach the end of its life cycle, it would instead become a white dwarf. Scientists estimate that there are around 40 billion black holes wandering in the universe, with many drifting through the Milky Way. With so many black holes roaming the cosmos, each possessing immense gravitational pull, could they one day pull Earth into their grasp? Black holes in the universe can be divided into two types. The first type consists of black holes formed from massive stars with masses up to 100 times that of our Sun. Without even needing to pull Earth in, the gravitational field of these black holes could disrupt Earth's orbit if they were to pass close enough. However, there's no need to panic about these black holes. Despite their immense mass, their radii are only about 300 kilometers, and the likelihood of one coming near Earth is almost zero due to the vastness of the Milky Way. The second type, however, is the true danger we should be concerned about. These are called supermassive black holes. Compared to the Sun, these black holes have masses millions or even billions of times greater. Their event horizons can span billions of kilometers. Supermassive black holes reach their colossal sizes by consuming vast amounts of matter in the universe and merging with other black holes. Unlike stellar black holes, Supermassive black holes are not wanderers. They are anchored at the centers of galaxies, including our very own Milky Way galaxy. Our solar system currently maintains a stable orbit around a supermassive black hole at a safe distance of 25,000 light-years. However, this stability could completely change if our galaxy collides with another galaxy. In such an event, Earth would most likely be consumed. This possibility could arise from a future collision with the Andromeda galaxy. For now, at least until we are long gone, we remain safe from the black hole. The story of black holes merging has also been a scientific challenge to demonstrate. In 2015, through the LIGO experiment, scientists for the first time recorded the sound of two black holes colliding. This served as vivid evidence of a pair of black holes about to merge, supporting the hypothesis that a larger black hole is formed from the merger of two smaller ones. After relentless efforts spanning many years, the first image of a black hole was captured. This was a supermassive black hole located at the center of the M87 galaxy. The image was taken using the Event Horizon Telescope, a network of 8 radio observatories scattered across 6 mountain peaks and 5 continents worldwide. Our Milky Way galaxy also has a black hole at its center, known as Sagittarius A star. This supermassive black hole was discovered within our galaxy. The actual image of Sagittarius A star, captured from this black hole, resembles what scientists had predicted. Although the existence of black holes has been confirmed, many mysteries about them remain unsolved. One of the most intriguing is the innermost region of a black hole, known as the singularity, which has led to various theories about time travel that we often hear about. Could black holes have an impact on the fabric of space and time around us? At the University of Nottingham in the United Kingdom, researchers have studied how black holes affect space and time by using a water tank. In the tank, they created a vortex to simulate a black hole. They then used a wave generator on the water's surface to simulate space and time in a vacuum environment. The ripples passing through the vortex were bent and drawn into it, demonstrating that a black hole can warp space and time at its location. This concept of a region where space and time are warped has been experimentally validated and aligns with Einstein's theory of general relativity. According to this theory, time moves more slowly for objects in a strong gravitational field compared to a weaker one. As we know, black holes have extremely strong gravitational fields. Therefore, when approaching the photon sphere surrounding a black hole, time slows down significantly. It slows to such an extent that as one nears the event horizon, time could appear to stop altogether. However, this is only from our perspective. From the perspective of someone approaching the black hole, time would seem to pass normally. This phenomenon is a part of Einstein's theory of general relativity, which explains how time can bend, speed up, or slow down, depending on the observer's point of reference. However, given the vastness of the universe, scientists can currently only observe black holes from the outside. Approaching them or conducting direct experiments remains an incredibly challenging task. Black holes are beyond our reach, and we cannot be certain that the equations we use truly describe a black hole. This inability to directly test our theories presents a significant challenge for scientists today. But does anyone wonder about the fate of a black hole? According to quantum physics, space is filled with pairs of photons, specifically photons and their antiparticles. Physicist Stephen Hawking theorized that particles with positive energy are ejected from the black hole, while particles with negative energy are absorbed into the event horizon. This causes the black hole to gradually lose energy and eventually evaporate from the universe. This process could take tens of billions to trillions of years. However, This theory has yet to be experimentally verified. Hawking once remarked about black holes, "People say that reality is sometimes stranger than fiction, and nothing could be truer when it comes to black holes." A shocking clip recently released by NASA reveals haunting sounds emanating from a monstrous black hole. The eerie sound resembles a strange, wild howl, as if from a terrifying, ferocious, and unidentifiable creature, with an undertone of rage. This monstrous black hole is a supermassive one, with a mass ranging from hundreds of thousands to billions of times that of our Sun. It is located at the center of the Perseus galaxy cluster, approximately 250 million light-years away from us, and containing thousands of galaxies. The sounds emitted are the result of explosions originating from the black hole at the center of the cluster. The acoustic waves generated were amplified by 57 and 58 octaves to make them audible, as the original sounds were far too low for the human ear to perceive. The results, released by NASA, include a graphical depiction of the Perseus galaxy cluster containing the monstrous black hole. This visualization was based on composite spectral data collected by NASA and other space agencies and astronomical telescopes worldwide. The clip serves as a reminder. While it is true that you cannot hear sound in the vast expanse of space, it doesn't mean there is no sound at all. In fact, the universe is extremely noisy and chaotic. It's just that human ears are not equipped to perceive it all. The acoustic waves traveling 250 million light-years from the center of the Perseus galaxy cluster were first detected in 2003. However, it is only recently that scientists succeeded in fully capturing these waves and converting them into something humanity can appreciate. Scientists have just identified a chilling new behavior of monstrous black holes that could destroy worlds like Earth right from their infancy. A time-reversed study led by Dr. K. Ito from the Graduate University for Advanced Studies in Japan analyzed data from the Cosmic Evolution Survey, COSMOS, to investigate the worlds of primordial galaxies. COSMOS is a massive data repository created using observations of distant regions of the universe with some of the most powerful telescopes on Earth. The research team studied galaxies that existed billions of years ago by observing their light, which took an equivalent amount of time to reach telescopes due to the vast distances involved. They also searched for X-ray and radio signals from active black holes. What they discovered was terrifying. Some monstrous black holes, supermassive black holes at the centers of galaxies, were not functioning as the hearts of their galaxies. Instead, they were destroying their own galaxies. In these unlucky galaxies, instead of undergoing the normal star formation process that produces stars and, eventually, planets, as the Sun and Earth were formed, everything was prematurely destroyed. The galaxies, which should have been teeming with life and activity, became lifeless and desolate instead. If black holes don't devour the seeds of stars or planets directly, they extinguish their formation right from the womb. Stars are born when cold molecular clouds of hydrogen collapse, fragment, and condense within galaxies. However, in unfortunate galaxies, their monstrous black holes emit such intense radiation from the swirling matter around them that they heat these molecular clouds, preventing them from collapsing and condensing to form stars. In some cases, the radiation even blows these gas clouds out of the galaxy entirely. Such galaxies become red galaxies, with only a sparse number of remaining stars that endure for long periods but are cold and lifeless. Most of these unlucky galaxies are massive elliptical galaxies, some of the oldest in the universe. Like all galaxies, our spiral galaxy, the Milky Way, also hosts a monstrous black hole known as Sagittarius A at its center. Fortunately, Despite its incredible power and ferocity, it has evolved in a way that supports the Milky Way's robust star formation process. The seeds of Earth were left undisturbed and not blown into interstellar space. Sagittarius A is currently in a dormant state, though it occasionally awakens to devour unlucky objects that stray too close. Recently, scientists have, for the first time, discovered a supermassive black hole ejecting material 50 times larger than its host galaxy. The monstrous black hole at the center of the galaxy, NGC 2663, might be one of the most extraordinary supermassive black holes in the universe. Astronomers from Western Sydney University used the ASCAP, Australian Square Kilometre Array Pathfinder, radio telescope system, developed by the Commonwealth Scientific and Industrial Research Organization, CSIRO, to identify this fascinating supermassive black hole. ASCAP, with its network of 36 linked radio dishes, forms a single, super-powerful telescope located in the remote desert of Western Australia, and is one of humanity's most advanced astronomical observation tools. The radio data collected by ASCAP revealed an unimaginably massive jet of material stretching over 1 million light-years across space, originating from the center of NGC 2663, an elliptical galaxy located 93 million light-years away. This colossal jet of material is 50 times larger than the Milky Way galaxy, and was ejected from the galaxy's central black hole. These jets are streams of extremely high-energy matter expelled by the black hole. While astronomers have observed many such jets before, none have matched the scale of this one. Not only is it exceptionally large, but its size also dwarfs the parent galaxy by a factor of 50. This jet also contains massive diamond shock particles, bright diamond-like points of light that shine brilliantly as they travel through the jet, glowing brighter than the surrounding material. This phenomenon suggests that the black hole ejecting the jet must be extraordinarily massive and powerful, potentially one of the largest black holes in the entire universe. Additionally, the effect is enhanced by the dense intergalactic material surrounding NGC 2663, which interacts with the jet to produce such a spectacular display. All of this creates a cyclical flow of matter between galaxies. Material enters a galaxy, is consumed by the supermassive black hole at its center, and then ejected as jets into the intergalactic space. These processes help galaxies across the universe to grow and evolve. The universe was shaken when a monstrous black hole unexpectedly flipped its magnetic field, a phenomenon never before observed in such a massive object. This dramatic reversal occurred in a galaxy billions of light-years away. While magnetic field reversals are not unusual in smaller celestial bodies, Earth itself has reversed its north and south magnetic poles hundreds of times, and the Sun undergoes an 11-year cycle of magnetic flips. This was previously thought impossible for supermassive black holes. However, the puzzling changes in the galaxy 1ES1927+654 have now been recorded. Known for its brightness since its discovery, the galaxy had been observed by the Swift telescope, which captured its X-ray and ultraviolet emissions. In 2017, it began to mysteriously brighten. Initially, scientists hypothesized that a large star had passed too close to the black hole, but this would have resulted in the star being torn apart, with disruptions to the gas in the black hole's accretion disk, neither of which were observed. Thus, the star disruption theory was dismissed. Subsequently, a research team led by Dr. Sebasish Laha from NASA discovered a rapid decrease in X-ray emissions from the galaxy. X-rays are typically generated by charged particles spiraling within a magnetic field, so this indicated a sudden change in the black hole's magnetic field. They also observed an increase in visible and ultraviolet light, suggesting that parts of the black hole's accretion disk were heating up. The only plausible explanation is that the black hole experienced a magnetic field reversal. This flip caused the magnetic field to weaken temporarily before resetting, during which the accretion disk became more efficient, making the black hole even more powerful. Such a reversal would have a profound impact on the surrounding region, significantly disrupting the galaxy and its neighboring objects. To search for the greatest power in the universe, humanity had to use everything at its strongest. Employing a telescope the size of Earth, we scoured every corner of the universe for 13 years. Hard drives brimming with massive amounts of data were transported by airplane and analyzed using the most advanced supercomputers. Finally, for the first time, we captured the first ever image of a black hole. A truly astonishing achievement. A black hole, or Ho-Gen, is the term used to describe a region of spacetime where the gravitational field is so strong that nothing, not even particles of matter or electromagnetic radiation like light, can escape it. Surrounding a black hole is a boundary defined by mathematical equations, known as the event horizon. Beyond this point, once matter crosses it, there is no way to escape the black hole. The concept of black holes was first proposed by an Indian physicist based on theoretical calculations. He demonstrated that stars with a mass greater than 1.4 times that of the Sun, after burning through nearly all their hydrogen, would collapse under the force of their own gravity and become black holes. This discovery sparked significant controversy. Arthur Eddington, who provided proof for Albert Einstein's general theory of relativity, did not believe in the existence of black holes. Similarly, the prominent Russian physicist Lev Landau considered the concept pure fiction. They argued that there must be some mechanism preventing gravitational collapse. Even Albert Einstein himself doubted the existence of black holes in the universe. As a result, until the 1960s, black holes remained a mathematical curiosity, lingering only in the minds of a few theoretical physicists. Very few were familiar with the concept of gravitational collapse. Observational techniques and tools at the time were still in their infancy. Telescopes were not powerful enough, sensors lacked the necessary sensitivity, and astronomical data was scattered and incomplete. No one knew how to detect a black hole, let alone observe one, a prospect that seemed entirely out of reach and utterly implausible. However, certain events led to a significant and unexpected shift. In 1963, American astronomer Martin Schmidt made a groundbreaking discovery. He identified quasar 3C273 at visible wavelengths. The spectral lines from 3C273 showed an extraordinary redshift, prompting Schmidt to exclaim in astonishment. This was a remarkable discovery, as no ordinary star could produce such a result. The Milky Way galaxy spans approximately 100,000 light-years, yet 3C273 is located 2 billion light-years away. It could not be a star within our galaxy. A single star that far away would be faint and almost impossible to observe. Instead, the source of light must be a quasar, a celestial object so incredibly powerful that it could appear as bright as it did from such an immense distance. Two renowned astronomers, Fred Hoyle and William Fowler, suggested that such quasars must possess an extraordinarily large mass, millions of times greater than that of typical stars, comparable to the mass of an entire galaxy. Theoretical physicist Richard Phillips Feynman pointed out that with such immense mass, these quasars could only be black holes formed by gravitational collapse. In 1967, astrophysicist Jocelyn Bell Burnell, while still a doctoral student, accidentally discovered pulsars through radio wavelengths. People were puzzled by the phenomenon. What could emit such precise radio pulses with cycles so incredibly stable? Subsequently, Franco Pacini proposed that pulsars might be related to supernova explosions. Later observations revealed that pulsars were likely neutron stars, the remnants of stars after they died, left behind after undergoing gravitational collapse. John Wheeler, a theoretical physicist from Princeton University, recounted that during a physics lecture in late 1967, a student suggested using the term black hole to describe objects of immense mass, such as quasars and pulsars. Wheeler agreed, and from that moment, black hole, much like Big Bang before it, entered the public imagination and became embedded in popular culture. By the early 1970s, theoretical research on black holes experienced a renaissance. This resurgence was driven by the calculations of theoretical physicists Jacob Bekenstein at Princeton University and Stephen Hawking at Cambridge concerning entropy and black hole radiation. Their results were groundbreaking, pushing the boundaries of imagination and providing significant momentum for both theoretical and experimental research on black holes. Black holes began to be used as theoretical tools to explore new ideas about quantum gravity, the nature of spacetime, and, most recently, and most unexpectedly, their connection to quantum mechanics. These theoretical advancements, along with the discovery of quasars and pulsars, rendered previous skepticism about the existence of black holes obsolete. They also forced experimental scientists to confront the seemingly impossible mission of proving the existence of black holes. The discovery of black holes is one of the greatest challenges in astrophysics. It required an extremely large system of telescopes, highly sensitive sensors, and an exceptionally high data transfer rate. This work demanded the perseverance of generations of scientists, culminating in the first ever direct image of a black hole, which definitively confirmed its existence. This historic achievement was unveiled on April 10, 2019, captured by the Event Horizon Telescope, EHT. The image reveals streams of plasma orbiting a supermassive black hole at the center of the M87 galaxy. The bright region in the image indicates where plasma is moving toward us. Since the plasma travels at nearly the speed of light, it appears brighter as it approaches us, while the dimmer region above it corresponds to plasma moving away. This phenomenon is known as relativistic beaming. From the image, scientists inferred that the plasma rotates clockwise and takes about 2 days to complete an orbit. What we are observing is the black hole in electromagnetic waves with a 1.3 millimeter wavelength, specifically in the radio spectrum. You can see some light rays from behind the black hole being bent and curving around its orbit. When sufficient light from all the hot gas swirling around the black hole is collected, it forms a visible ring, a visual representation of the black hole's location relative to us. This ring, gradually becoming clearer in the image, aligns precisely with what Einstein predicted over 100 years ago. The supermassive black hole in M87 is highly active, meaning it constantly consumes large amounts of matter from its intensely hot accretion disk. However, it also emits powerful jets of high-energy particles and radiation from its poles, driven by its rotation and extremely strong magnetic fields. These jets extend at least 5,000 light-years, and one of them appears to be nearly aimed directly at us. This can be observed more clearly in this image from the Hubble Space Telescope. The black hole in this image has a mass 6.5 billion times that of our Sun. Incredible, isn't it? More than 6 billion suns compressed into a single point, dominating part of the energy dynamics at the center of this galaxy. This black hole is enormous. Its actual size is roughly comparable to that of our solar system. However, it is located 53.5 million light-years away, making it extremely challenging to capture its image. Scientists needed an extraordinary solution. Black holes are the smallest objects in the visible universe, yet they exert an enormous influence on entire galaxies. To observe a black hole, you would need a telescope the size of Earth. Scientists synchronized telescopes around the globe with perfect precision, using atomic clocks to capture the light waves emitted from this black hole. They then combined all the collected data to produce the image. A massive amount of data was required to create this photograph. As you can see, these are the hard drives containing half of the data collected by the Large Millimeter Telescope, situated atop a mountain over 4,500 meters high in Mexico. This data amounted to nearly half a petabyte, equivalent to all the selfies taken over a lifetime by around 5,000 people. And this is only a fraction. Much more data was collected from other locations. All of this was transported via airplanes because it could not be sent over the internet. In total, 5 petabytes of data were gathered to produce the first ever image of a black hole. After 3 years of success, following the capture of the first black hole image, on May 12th this year, scientists unveiled the first ever image of the supermassive black hole Sagittarius A, located at the center of our galaxy. This mysterious object, situated more than 27,000 light-years from Earth, is estimated to be 4 million times the mass of the Sun. While its existence had been hypothesized for a long time, it had never been observed until now. The image serves as the first direct evidence confirming the existence of Sagittarius A star. The existence of Sagittarius A star was first hypothesized in 1974, following the discovery of an unusual radio source at the center of the Milky Way. By the 1990s, astronomers had mapped the orbits of the brightest stars near the galactic center, providing further indirect evidence. Sagittarius A star bears striking similarities to the black hole at the center of the galaxy, Messier 87. Both behave as predicted by Einstein's general theory of relativity, formulated in 1915. Despite being much closer to Earth at 27,000 light-years compared to M87, capturing an image of Sagittarius A star posed a far greater challenge. The gas near both black holes moves at nearly the speed of light. However, while it takes days to weeks for gas to orbit the much larger M87, it only takes a few minutes to complete an orbit around Sagittarius A star. The research team developed new, more sophisticated tools to calculate and capture the images of these rapidly changing and dynamic targets. Scientists are eagerly comparing the two black holes to test theories about how gas behaves around them, an as yet poorly understood phenomenon that may play a role in the formation of new stars and galaxies. The colossal size of the largest black hole in the universe. How large do you think the biggest black hole in the universe is? A. The size of the Sun. B. Larger than the solar system. C. The size of a galaxy. D. More than 40 billion times the mass of the Sun. Please comment below to let us know your thoughts. When it comes to the largest things in the universe, we must mention black holes. Unlike objects such as planets or stars, black holes have no physical size limit and can grow infinitely, literally. However, in reality, certain specific conditions are required to form different types of black holes, ranging from very small ones to the largest giants in the universe. So, how do black holes grow, and how large can the biggest of them get? Let's start with something truly, truly small. Primordial black holes. The smallest type of black hole that might exist, or might not. If they do exist, they could be among the oldest objects in the universe. Even smaller than atoms, they would have formed right after the Big Bang when intense energy streams filled the dense, chaotic universe. In such conditions, any small region with a slightly higher density than its surroundings could potentially create a black hole. The smallest primordial black holes that might exist could weigh about 1 trillion kilograms, roughly equivalent to the mass of a large mountain. However, their size would not be larger than a proton. A primordial black hole with the mass of Earth would only be slightly larger than a coin. This makes them extremely difficult to detect, which is why we haven't directly observed them yet. If they do exist, they might even be the mysterious dark matter that holds galaxies together. Let's move on to the type of black holes we know for certain exist: stellar black holes. To create a black hole, we need to compress enough matter so that it collapses under its own gravity. The more mass that is pulled in, the larger the black hole becomes. In the modern universe, only the most violent cosmic events can create the necessary conditions for their formation, such as the merger of neutron stars or the collapse of the core of a massive star during a supernova. To provide a point of comparison, we'll use the mass of the Sun, which is about 2,000 trillion kilograms. The smallest known black hole, GW 170817, has a mass 2.7 times that of the Sun. It is shaped like a sphere with a diameter of about 16 kilometers, large enough to cover the entire city of Paris. A lighter black hole is the companion of the giant red star V723 Mon. This star is 24 times more massive than our Sun, with a diameter of 30 million kilometers. It is orbited and tormented by a small black hole nicknamed the Unicorn, which is just 17.2 kilometers wide. This tiny black hole bullies the massive star, and its size is so small that it's difficult to find anything comparable. One of the largest known stellar black holes is M33X7, currently consuming a massive blue star 70 times the mass of the Sun, bit by bit. As the stolen matter spirals toward the black hole, much like water swirling down a drain, friction heats it to temperatures high enough to shine 500,000 times brighter than our Sun. M33. X7 itself has a mass of 15.65 suns and a width of 92 kilometers. To grow larger, black holes must devour massive numbers of stars or merge with other black holes, which is a much faster process. The tools we use to detect these mergers are relatively new, which is why we are now discovering so many fascinating phenomena. For example, 2 enormous black holes were found in a galaxy 17 billion light-years away. As they violently orbited each other, they released more energy in the form of gravitational waves than the combined light of all the stars in the Milky Way over 4,400 years. The newly formed black hole, named CW10521, is about the size of Germany and has a mass 142 times that of the Sun. Here, we've reached a truly astonishing scale of the universe. There are many black holes with masses up to 150 times that of the Sun, and then, suddenly, there's nothing for a long stretch until we encounter black holes with masses millions of times larger. This is puzzling because we've assumed that black holes grow gradually over time. However, for the largest black holes, this process isn't fast enough to explain their existence today. Simply put, the universe isn't old enough for these supermassive black holes to have formed solely by consuming stars and merging with one another. Clearly, something else must have happened. To explain how we got the largest black holes in the universe, we might need to consider the largest stars that ever existed: black hole stars. For scale, we can compare them to the largest stars that exist today. Our Sun would appear like a grain of sand next to them. Scientists aren't sure if black hole stars actually existed, but they represent a fascinating concept. When it comes to the rapid growth of black holes, the idea is that in the dense early universe, matter was so abundant that black hole stars could potentially be thousands of times the mass of our Sun. The cores of these stars might have been crushed by their own immense weight, collapsing into black holes while the star itself was still forming. Unlike modern stars, which destroy themselves in the process, these stars could have enabled black holes to grow at extraordinary speeds. Inside black hole stars, a deadly balance could exist within black hole stars. Gravity compresses the massive star, feeding the black hole at its core and heating the infalling matter to such high temperatures that radiation pressure stabilizes the star. As a result, these rapidly growing black holes might have consumed their host stars over millions of years, growing far larger than any modern stellar black holes. These black holes could have masses thousands of times that of the Sun and diameters larger than the entire Earth. These black holes may have become the seeds for today's supermassive black holes. Now we arrive at the kings of the universe, the largest single entities in existence. The centers of most galaxies host a supermassive black hole, each one extraordinary in its own right. In our Milky Way, we have Sagittarius A star, a supermassive black hole with a mass roughly 4 million times that of the Sun. It is calmly gathering material and performing its cosmic duties. We know it is there because we can observe a star orbiting what appears to be an empty point in space. Despite its immense mass, its radius is only about 17 times that of the Sun. Smaller than most giant stars, but millions of times heavier. Because supermassive black holes are so massive and located at the centers of galaxies, many imagine them to be like the Sun in the solar system, a central anchor binding everything together and forcing it into orbit. However, this is a misconception. While the Sun accounts for 99.86% of the total mass in the solar system, supermassive black holes typically make up only 0.001% of their galaxy's mass. The billions of stars within galaxies are not bound by the gravitational pull of the black holes. Instead, it is the gravitational effects of dark matter that hold them together. Many supermassive black holes are not gentle giants, especially when they consume large star-forming clouds in their galaxies. The black hole at the center of the galaxy BL Lacerti, for instance, is devouring so much matter that it generates plasma jets accelerated to nearly the speed of light. If Earth were orbiting this colossal object, it would appear 115 times larger than our Sun in the sky, and we would be incinerated within seconds by its blazing accretion disk. At this scale, black holes become so massive that stars appear strangely tiny in comparison. The galaxy Cygnus A hosts a supermassive black hole with a mass 2.5 billion times that of the Sun and a diameter of 14.7 billion kilometers. If it replaced our Sun, it would engulf all the planets and extend to nearly half the edge of our solar system. It consumes so much mass and material that its accretion disk acts like a cosmic funnel, ejecting gas outward to form gigantic radiolobes towering above the galaxy, spanning 500,000 light-years in diameter, 2.5 times the size of the Milky Way. Another supermassive black hole resides in galaxy M87, with a mass of 6.5 billion suns. This was the first black hole ever captured in an actual image, or more precisely, the glowing gas around the edge of its menacing shadow. This sphere of darkness is so immense it could encompass our entire solar system. But there's an even greater scale: ultramassive black holes, perhaps the largest single objects to ever exist. These black holes have consumed so much that they've grown to tens of billions of times the mass of the Sun. Their gravity powers quasars, accretion disks that shine brighter than thousands of star-filled galaxies combined, deserving a title of their own: ultramassive black holes. At the center of the galaxy, OJ-287 lies an ultramassive black hole with a mass 18 billion times that of the Sun. It's so large that a supermassive black hole nearly 40 times the size of Sagittarius A orbits around it. It is truly difficult to compare it to anything else. 3 solar systems could comfortably fit inside this black hole. Tawny 618, a black hole we can observe, is consuming an amount of matter equivalent to several galaxies, shining with the brightness of 100 trillion stars, visible from a distance of 10 billion light-years. Its mass is an astonishing 66 billion times that of the Sun. This black hole is so immense that it would take light an entire week to reach the singularity after crossing the event horizon. Approximately 11 solar systems could fit side by side within it. It is very likely the largest single object in the universe, but in reality, it might be even larger because Tawny 618 is so distant that what we see is how it looked 10 billion years ago. In any case, black holes are terrifying, mysterious, and colossal. They will remain long after everything else has perished, growing ever larger over time. Finally, we arrive at the King of Kings, a mysterious black hole located in the Phoenix Cluster, a galaxy cluster situated 5.7 billion light-years from the Milky Way. Discovered by the South Pole Telescope in 2010, this cluster is one of the largest galaxy clusters known and one of the most X-ray luminous clusters ever observed. The central galaxy of the Phoenix Cluster is Phoenix A, an elliptical galaxy. At its core lies a supermassive black hole, Phoenix A, with an estimated mass 100 billion times that of the Sun, making it the largest known black hole and surpassing what was thought to be the theoretical mass limit for such objects. However, we don't have absolute certainty about this. While scientists have cataloged millions of stars, they only have accurate data on a few dozen black holes. This is because the study of black holes didn't gain significant attention until 50 years ago, and even now, it remains technically challenging. Since we cannot directly observe black holes, we can only infer their properties by studying their gravitational effects on surrounding matter, such as the orbits of stars near them. These effects depend on the black hole's mass, allowing us to estimate their mass using basic principles like Kepler's laws. But this method comes with significant uncertainty and errors. Scientists then convert the estimated mass into size, introducing additional inaccuracies. For example, they calculate the radius from the mass using the Schwarzschild equation, simplifying and assuming that black holes are perfectly spherical and non-rotating, a condition that doesn't truly exist. The reality is that the physics at these scales is somewhat ambiguous. As a result, some of the black holes we've discussed here might be significantly smaller or larger than currently estimated.